A blowout. Gas, oil, salt water flowing out of control. Pretty awesome. But you know, before a well blows out, it kicks. Formation fluids enter the hole. These fluids force or kick mud up the well bore. If you don't take the right action right now, your rig could wind up like this. So you have to contain a kick. And that's what the blowout preventers are for. When closed, they contain the kick. A closed preventer seals off the top of the well. It's like closing the valve on a pipeline. With the BOP closed, no more kick fluids can enter the hole. Back pressure from the closed preventer plus the hydrostatic pressure of the mud balances formation pressure. No more formation fluids can flow into the well. And that's why you have to close in the well when you detect a kick. But you got to know what you're doing. Use the preventers carelessly and you could cause problems. You could even lose the hole. So let's find out more about well control. Here's some of the major causes of kicks. Mud weight not heavy enough, not keeping the hole full of mud, and swabbing the hole. Let's look at these in more detail. First thing is mud weight. The mud's got to be the right density or weight at all times. Otherwise, this could happen. The mud won't put enough pressure on the formation, and formation fluids enter the hole. Of course, the heavier the mud is, the more pressure it exerts. But you have to use mud that's the right weight. In fact, drilling's usually done with mud as light as possible. The rate of penetration is faster with light mud, so the possibility of a kick is always present. Also, wells are being drilled deeper than ever, and the deeper you drill, the more likely you are to penetrate zones of high pressure. Drilling into a deep high-pressure zone could mean that the hydrostatic pressure exerted by the mud is too low to hold back formation pressure. For example, here the hydrostatic pressure is 5,400 psi, but the formation pressure is 5,800 psi. The well's kicking. The mud weight is not heavy enough to hold back the formation pressure. So you got to watch out for high pressures when you're running that brake. Okay, so much for drilling, but nearly half of all kicks occur during a trip. So, to avoid kicks while tripping, be sure to condition the mud before you start out of the hole. And as the pipe is tripped out, keep the hole full of mud. Keep the hole full at all times. Remember, hydrostatic pressure depends on the height of the mud column as well as its density. So when you make a trip, slug the pipe so it'll pull dry. This keeps mud in the hole where you need it. Also, carefully measure the mud pumped in to replace the volume of pipe pulled out. Point is, keep the hole full of mud. Another problem during trips is swabbing. The bit and drill stem can act like a swab or piston and pull formation fluids into the hole. Here the hole's full, but not of pure mud. Swab in enough formation fluids and you reduce the hydrostatic pressure. The result could be a kick. So what do you do to reduce swabbing? Well, when the mud's real thick or viscous, swabbing is more likely to occur. So when you can, keep the mud's viscosity down. Also, when your mud weight gives you only a small hydrostatic overbalance, watch out for swabbing. Swabbing is more likely, too, when the bottom hole assembly is pretty close to the size of the hole. In effect, the piston's bigger, and it'll be more likely to swab. And if you pull the pipe out of the hole too fast, you're more likely to swab formation fluids into the hole. So be sure to properly condition the mud before you trip out and pull the pipe slow enough to minimize or prevent swabbing. Here's one way to know that you've swabbed. You'll notice that less mud is needed to fill the hole because of the swabbed-in fluid. Keep handy a table of displacement volumes for drill pipe and drill collars. This one shows drill pipe displacement in barrels per 90-foot stand and drill collar displacement in barrels per 30-foot joint. For instance, reading left to right, if you're pulling 4.5-inch 16/6 IF drill pipe, each stand displaces a little over half a barrel, 0.57 barrels to be more exact. You can use a trip tank to measure the number of barrels it takes to fill the hole. This is the most accurate way. But you can use a pump stroke counter, even though it's not as accurate as a trip tank. A trip tank is just a small mud tank with some sort of mud level gauge on it. The mud level in the tank should drop as each stand or row of stands is pulled. It should drop by an amount equal to the volume of pipe pulled out of the hole. If it drops less, then you can figure you probably swabbed formation fluids into the hole. You can also use pump stroke counts to calculate hole fill-up because a mud pump is like a positive displacement meter. In other words, each time the pump strokes, it puts out a given amount of mud. Using the pump's liner size and stroke length, you can figure out how many strokes it takes to put 1 barrel of mud into the hole. Of course, if swabbing's occurred, the pump takes less strokes than it should to fill the hole. By the way, you can't really use the regular mud pits to measure in fill-up mud. Trouble is, the level in a large pit won't change very much until a lot of mud has been added to the hole. Lost circulation is another problem that's kind of related to swabbing. How? Well, as you know, if you move the drill stem too fast when coming out of the hole, you may swab. Similarly, when going in, just like when coming out, the bit and drill stem can act like a swab or piston and create a pressure surge as the drill stem goes down the hole. And sometimes a pressure surge can cause lost circulation. The surge breaks down or fractures the formation. Thus, the mud level in the hole falls, reducing hydrostatic pressure. And if a high-pressure formation is open to the well bore, then formation fluids enter it, causing a very dangerous situation. So be sure to run the pipe back in the hole at a slow enough speed to minimize pressure surges. Also, make sure the mud is well conditioned. Its viscosity, gel strength, and wall cake thickness all affect how big the pressure surges will be. If workbooks are available, stop the cassette and work exercise 1. After working the exercise, return to the second part of the program. So far, you've seen some of the things that can cause kicks, but how can you tell when you take a kick? Well, some of the signs of a kick while drilling are a drilling break, an increase in the mud return flow rate, an increase in pit volume, a decrease in pump pressure, an increase in pump speed, a chloride increase, gas cut mud, and a change in cutting size. A drilling break is an increase in the rate of penetration. The increase can be spectacular. The bottom drops out. Or it can be minor, like from 6 minutes a foot to 5 minutes a foot. But spectacular or minor, a drilling break may indicate a kick, because a kick lifts cuttings off the bottom very efficiently. The bit starts working on uncut formation, so the rate of penetration increases. Another sign of a kick is an increase in the return flow rate of the mud. Increased return flow is a good sign of a kick because anytime formation fluid enters the hole, it causes the mud above it to flow out faster. A return flow sensor is a useful tool to help you see an increase in return flow. This one has a paddle sensor in the return line that moves as mud flows past it. It sends a signal to a meter on the rig floor where flow is shown as a proportionate reading. If flow increases, the meter can warn the driller. Of course, if the return flow increases, then it'll only be a short time before there's a gain in pit volume. So it's really good if your rig has a pit level indicator to warn of a pit gain or loss. Also, it's good to have unscheduled pit level or flow sensor drills so that everyone knows what to do when a real kick happens. Another sign of a kick is a chloride increase. The mudman can detect a chloride increase. It could mean that you've taken a salt water flow downhole. Gas cut mud may also be a kick warning sign, but often it's not. Thing is, a little bit of gas that enters the hole at the bottom expands fast as it circulates up the hole. In fact, what's only 1 cubic foot of gas at bottom expands to over 1,000 cubic feet at the surface. Gas expands rapidly as hydrostatic pressure on it is reduced. So what can be a lot of gas on the surface probably isn't very much on bottom. But be sure to degas the mud. If you don't, you run the risk of cratering your pump from severe knocking. Still, another sign of a kick can be a decrease in pump pressure and a corresponding increase in pump speed. What happens is that when kick fluids enter the well bore, they lighten the mud column. It's easier for the pump to move mud that's been made lighter by kick fluids. Another possible sign of a kick is a change in the size of the cuttings. For instance, sometimes shale formations are abnormally pressured. When drilled, the shale sloughs or heaves, and the pieces are circulated to the surface. At the shaker, the heaving shale can show up as long slivers. So, what do you do when you think you may have taken a kick? Well, don't ever hesitate. Anytime you suspect that a well has kicked, pick up off the bottom, shut down the pump, and see if the well continues to flow, even with the pump off. If it does flow with the pump off, you've definitely taken formation fluid into the well bore, so shut the well in. These are the first steps in controlling a kick. There are more, but for right now, stop the tape cassette and work exercise 2. After working the exercise, return to the third part of the program. So far, you've seen what causes kicks and some of the signs of a kick. Now let's go one step farther and take a look at what happens when you shut the well in on a gas kick. Let's say a large gas slug enters the well bore from a high pressure formation. All the signs of a kick are present. This isn't gas cutting, this is a kick. You've shut in the well to stop the flow of fluid, but no one knows what to do. So the gas slug will rise up the hole. It rises because it's so much lighter than the mud, but it can't expand. The well's completely shut in. The gas pressure is the same as formation pressure. In this case, let's say 5,800 psi. This is because you shut in the well as soon as the gas entered. The 5,800 psi gas pressure is offset by the hydrostatic pressure of the mud column, 5,400 psi, plus the 400 psi shown on the drill pipe gauge. This is back pressure being held on the well by the closed preventer. The shut-in pressure of 400 psi plus the hydrostatic pressure of 5,400 psi equals a bottom hole pressure of 5,800 psi. Everything's fine for the moment. But not for long. Because gas is so much lighter or less dense than mud, it rises up the hole. Here the gas has risen halfway up the hole. The well's still shut in, so the gas is not expanded. It still has the same 5,800 psi pressure it had when it first entered the hole. The gas pressure stays the same. So we have a problem. Look at the bottom hole pressure, 8,500 psi. That slug of gas halfway up the hole exerts 5,800 psi in all directions. So you have to add 5,800 psi to the 2,700 psi of hydrostatic pressure below the slug. That gives you 8,500 psi at bottom. Of course, there's the same amount of mud above the slug as below it. So the mud column above the gas slug also exerts 2,700 psi of hydrostatic pressure. But the gas pushes up 5,800 psi. What this means is the hydrostatic pressure of the mud in the top half exerts pressure against the gas bubble, leaving a difference of 3,100 psi. 5,800 less 2,700. This 3,100 psi is shown on the casing pressure gauge at top. Now the gas slug is all the way up to the top. It still has the same pressure as it had on the bottom, 5,800 psi. With the slug all the way up and not allowed to expand, bottom hole pressure is now a whopping 11,200 psi. This is the sum of 5,800 psi plus the mud column's hydrostatic pressure of 5,400 psi. Actually, though, the formation would have broken down long before the gas ever got to the top. This is why it's very important to know what to do after the well is shut in. Just remember, after the well is shut in, the gas bubble starts rising up the hole. As the gas rises, you have to have some way to open or vent the well to allow the gas to expand. But you can't open it too much. Back pressure would be reduced so much that the well would kick again. So here's a choke, a special valve with an opening you can adjust. By reducing or increasing the size of the opening, you can vent gas and mud from a shut-in well and keep the bottom hole pressure constant. In the next program, you'll get to see how to adjust the choke to properly circulate a kick out. But for now, stop the tape cassette and work exercise 3.